Hello everyone. This study is on unsupervised machine learning for interpreting shelf to slope to basin seismic geomorphology and paleoclimate. This study is based on a work that was conducted on North Slope, Alaska in the United States by me, Sumit Verma at University of Texas Permian Basin, and my colleague Dr. Shivajit Bhattacharya at University of Texas at Austin. Our study area is in North Slope, Alaska, which is very close to the Prudhoe Bay oil field, which is quite famous. And most of the oil fields in this region, they produce from formations from Mississippian to Triassic age. And the production from these areas are depleting with time. So in recent times, the good news came from say the discoveries within the Turok and Nanushuk formations, which are of Cretaceous age, and some of these discoveries are mentioned here. In 2015 we have Armstrong Rapsol's Pickers discovery with the 300 million barrels of oil. In 2017 ConocoPhillips's Willow discovery with the 750 million barrels of oil, whereas in 2017 Calus Energy's Smith-based discovery with 1.2 billion barrels of oil. Our study area is covered by 3 seismic surveys in NPRA, or National Petroleum Reserves in Alaska. So these surveys are NENPRA acquired in 2006, Harrison Bay acquired in 2006, also Harrison Bay acquired in 2004. With these 3 surveys, they cover approximately 2,500 square kilometer, and these surveys were acquired with a nominal fold of say 35 to 50, which is a decent seismic data quality. And these seismic surveys are available through Alaska DNR website through the tax credit program. For anyone who tries to obtain these surveys can approach them. In this study, we identified different geomorphological features from shelf, slope to deep marine settings and analyze their evolution over time. And to do so, we use seismic attributes and develop an ML based or machine learning based workflow to automate such process for the first pass of such geological interpretation. Before we go into the details of the seismic attribute study and some machine learning, I would like to explain a little bit about the geological deposition of Nanushuk and Turok formations, which are the formations of interest. And they were deposited in the shelf to basin setting as a part of Cretaceous age Brookian sequence. Here, Nanushuk formation forms the top sets of this sequence, and the Turok formation is the time equivalent of Nanushuk and forms the bottom sets here. So there are 2 sources of sands for these depositions. One is from the western side, from Siberian side, where you can see longer channels with the gentler slopes in the side, and in the other side it is Brooks Range, where the sands are coming, and you can see smaller channels with a steeper slope. We start our workflow by taking the 3D seismic data and computing the dip volume by using the robust 3D dip search method, and in which we compute dip magnitude and dip azimuth volume. We use this volume to compensate for the dip in coherence computation, which is a discontinuity attribute. And we also compute coherent energy, which is the first principal component of the seismic data that shows the energy state of, or the depositional energy environment of the deposition. And apart from that, we also compute the spectral decomposition, where we divide the seismic data into different frequency components. And we also compute the GLCM, the gray level co-occurrence matrix attributes, or the texture attributes. We take all these attributes into machine learning using the SOM, self-organizing, and divide the data into different classes or seismic phases. And further on, these seismic phases are extracted along different horizons that was picked on this seismic data, and also the straddle slices parallel to these horizons, and then create a 3D seismic interpretation view with these straddle slices as well as the cross sections of seismic amplitudes. We also extract the other seismic attributes along these horizons, and we make a final interpretation with the interpretation of all the geomorphological features on these 3D views. Let me start our results section. So first of all, I will show you a 30 miles long seismic cross section that covers all the three surveys. And here you can see Nanushuk formation on the top as a top set, and Turok formation as a bottom set. Here they are time equivalent formations. And you can also notice the prograding clinoforms from the west to east direction here. And you can notice different geomorphological features here. For example, slide scar is present here as a concave down feature, or you can also see the slumps here, which are showing tiny thrust faults here, or the sediment wave as a small undulations. And you can see a big scarp feature here. Apart from that, you can also see this slide blocks, and along with this velocity push down effects here, down there. In our study, we have used different seismic attributes. Seismic attributes can be defined as mathematical quantities derived from seismic. They can be derived from amplitude, geometry, texture, or frequency of the seismic data. So here we have four attributes: coherent energy, which is computed by computing the principal component of the data, and coherent energy is the square of the first principal component of the seismic data. And coherence is the um, attribute which shows us the discontinuities, and that is based on the waveform shape or amplitude. Here we are using Sobel filter similarity, which shows the changes or the discontinuities based on the waveform and amplitude changes. Also, we have homogeneity GLCM attribute, which shows the dissimilarity in the seismic data. And we have spectral decomposition, which divides the data into different frequency components. Here we have used the frequency component of 20 Hz, 35 Hz, and 50 Hz. Now let's look into our results. So this is the 3D view. Now you are looking at, so there is a wall here of seismic amplitude in this part as well as here, and you can clearly see the prograding clinoforms here. And also you can see the more horizontal reflections for the shelf area. And in the middle you can see the stratal slice of the coherent energy co-rendered with coherence. Here we are trying to show just the low coherence values. We hide all the high coherence values, so such that we can show all the discontinuities or the edges of the channels and some other features here. You can see the high coherent energy inside this canyon here, and that shows that the high energy environment is present here. That might be some sands coming in. Also you can see some channels which are more likely to be filled with the sands, as they are showing up with the high energy values. Also you can notice some sediment waves in this direction here. Now if we look at the RGB plot or the spectral decomposition of 20, 35 and 50 Hz seismic data together, you can see many different colors here. These different colors are present because different thickness sediments, they tune with the different frequency components. So you can see here this color here is very white because all the different components are present in this, and you can see a white color. Whereas if something is just tuning with the very small thickness things like blue colors, they are very thin sediments. So here in this part you can see that, or in the channels you can see the same thing here. but overall effect of this is that like you can see these channels more clearly, as well as you can see the sediments waves much more clearly compared to our coherent energy. So now let's understand the unsupervised basis classification. First of all, SOM or self-organizing map. In self-organizing map, we transform the data from a higher dimensional space to a lower dimensional space. We are here doing it on a two-dimensional space, SOM Latin space 1 and SOM Latin space 2. And in this process of transformation and SOM clustering, we are keeping the topology. The topology preservation means we are keeping the points with the same distance as they were in the attribute space. So now after they are transformed onto a two-dimensional space, what we do is we color them with a two-dimensional color scheme. And here we have 256 colors, and we color all these points based on their proximity. Here you can see that the closer colors mean that they are similar facies, and distance colors means they are different facies. So green and purple, they will be different from each other, whereas purple and then a slightly different shade of purple means they are very part of similar facies. Here to mention that the input for this SOM clustering was the attributes coherent energy, homogeneity, spectral decompositions, 20 Hertz and 35 Hertz of frequencies. Here you are looking at the SOM clusters image, and you can identify similar features as we had done in our RGB plot. And you see here the canyon, and most of those colors, if you look at the red and orange, they are showing these sand filled channels here, and this canyon is flowing them here. And apart from that, you can also see some sediment waves which are due to the longshore currents here in this direction, which are flowing say in north-south direction. And you can see these sediment waves in this side quite well, but in this part across the canyon you cannot see so well those the sediment waves. But you can again see some of those channels here in this direction. And now if you had to look at the other labels, we can go to that. So here if we go to the shallower level, we can see the sediment waves much more clearly. Here you can see they are continuing quite well, and even further shallower you can see these continuations much more clearly. There are some other channels and canyons which are still visible in this part. Now coming to the conclusions, we used a variety of seismic attributes to identify geomorphological features, and further we use these attributes in unsupervised machine learning algorithms to identify different clusters for geomorphological features based on their seismic response. And further we implement these human interpretation that geologists have to interpret the machine-based clusters. And such technique can make the interpretations much faster. Also, we utilize the spectral decompositions, the frequency volumes to identify thickness changes in the sediments. The thicker sediments which are happening in the canyon, they are tuning with the different colored or different frequency of spectral decomposition, whereas the thinner sediments which are in the sediment wave and the slope channels, they tune with the different kind of spectral decomposition volume. At the end, I would like to say this kind of study can be used for variety of studies, including say oil and gas, as well as the paleoclimate studies. I would like to thank Alaska Department of Natural Resources for providing the seismic as well as the well log data, and Schlumberger for providing the federal licenses which were used for seismic interpretation. Seismic attributes were computed on ASPE software, and we would like to thank all the ASPE sponsors for their financial support.